In the later part of the chapter, Electromagnetic Induction, we will be learning the concepts of AC generator, induction and energy transfer, Eddy currents, and the concept of inductors. AC generators. Let us see the components of AC generator. You require armature coil, slip ring commutators, strong horseshoe magnets, carbon brushes, and the axle to apply a torque. The armature coil is mounted in between the pole pieces of a magnet. This magnet produces the radial magnetic field. The ends of the armature coils are connected to the slip ring commutators. The brushes which are running on the slip ring commutators gathers the current from the armature coil. With the help of axle, the coil is rotated in a magnetic field with angular velocity omega. So when a coil is rotated with the angular velocity omega, the angle between the magnetic field vector B and the area vector A of a coil at any instant of time is theta, which is equal to omega t. At time t is equal to 0, we can assume theta is equal to 0. As the effective area of the coil is changing due to the rotation of the magnetic field B, the flux at any time can be written as phi of B is equal to BA cos theta. Theta can be written as omega t. So phi of B is BA cos of omega t. Armature coil has n turns. So using the Faraday's laws of electromagnetic induction, we can write E is equal to minus n d phi B by dt, which is equal to minus n d of dt of BA cos of omega t. As magnetic induction B is constant, area of coil is constant, the derivative will go on only on cos of omega t, and the derivative of cos omega t is minus omega sin omega t. Therefore, E is equal to NBA omega sin omega t. If we substitute sin omega t is equal to plus or minus 1 in the above equation, we get E is equal to plus or minus NBA omega, which will give us the peak EMF E naught. So we can write down E is equal to E naught sin of omega t. Substituting omega as 2 pi f, we get E is equal to E naught sin 2 pi ft, where f is the frequency of revolution of the coil. The adjacent figure shows the coil rotating in a magnetic field of induction. At different angles, the EMF generated is shown in the graph below the adjacent figure. Induction and energy transfer. Observe the figures carefully which are given at the left hand bottom. We can find that there is a rectangular loop of the wire kept in the magnetic field. If the same loop is pulled towards right with the force F, there is a relative motion between a coil and the magnetic field that gives rise to induced currents, and these induced currents will flow in a clockwise direction. This will result in a force F equal to ILB sin theta, and this magnetic force will oppose the pulling force. Therefore, the rate of doing work on the loop will be given by power, which is equal to force and velocity. As we are aware, power is the scalar product of force and velocity. Now, to work on the physics behind it, let us consider the magnetic field B, which is directed into the plane of the paper as shown in the figure 1. As the loop is pulled towards right, the area of the loop in the magnetic field decreases. Therefore, the magnetic flux linked with the loop also decreases. This decrease in the magnetic flux linked with the moving coil in the magnetic field induces a current in a clockwise direction. This induced current gives rise to force F1, which will act opposite to the direction of the motion of the loop. So if we use the Fleming's left-hand rule, we can find out the direction of the forces that are acting on the loop as F1, F2, F3 and F4. It's quite clear that F2 and F3 are equal in magnitude but opposite in direction, will cancel each other's effect, and only the opposing force will be F1 that will oppose the pulling force. Now, the magnetic flux that is linked with the coil is given by phi of B, which is equal to B into A, where A is the area of the coil. So area is length into breadth. Length of the coil in a magnetic field is X and the breadth of the coil is L. Therefore, the area can be written as L into X. Therefore, phi of B is B LX. Now, as the loop is pulled, the value of X goes on decreasing, which results into the decrease in the flux. Therefore, according to the Faraday's laws, the magnitude of EMF generated, mod of E is equal to mod of d phi by dt. And if you substitute the value of phi and take the first derivative with respect to time, we get the induced EMF equal to B LV. The above figure, figure 1, can be thought equivalent to a circuit with the total resistance of the coil equal to R and the current I flowing through the resistor I, and the induced EMF is E. We can assume that loop has a sufficient high resistance so that a small amount of current is generated. The induced EMF E is represented on the left of the figure, and the collective resistance of the entire loop is given on the right of the figure. The direction of induced EMF or current is given by the right hand rule. The magnitude of induced current I is equal to BLV upon R because it is equal to R E by R. So what is the magnitude of F1? That is the force that is opposing the pulling force. So mod of F1 is equal to ILB sine of 90, which is just ILB because sine 90 is equal to 1. And as only F1 is surviving, we can talk that force as the opposing force F, which is equal to ILB. Substituting the value of I, we get the magnitude of force F as BLV upon R into LV. So the opposing force F is equal to B square L square V divided by R. We know that power is a scalar product of force and velocity. Substituting the magnitude of force as B square L square V upon R and multiplying with velocity V, we get the power generated equal to B square L square V square upon R. Therefore, rate of production of heat energy is equal to I square R. So substituting the value of I square as BLV upon R bracketed square and multiplying it with R, we get the rate of production of heat energy as B square L square V square upon R. So let us draw the conclusions from the above equations. We find that the rate of doing mechanical work is exactly the same as the rate of production of heat energy in the circuit or in the loop of the wire. Thus, the work done in pulling the loop through the magnetic field appears as the heat energy in the loop. Now we will learn the concept of eddy currents or Foucault currents. We are aware of the eddies that are produced in the water, also known as the whirlpools in water. These eddy currents were first time discovered by the scientist named Foucault, and they are also called as the Foucault currents. Eddy currents are produced when the metal sheet is kept in a changing magnetic field as shown in the figure. If you place a metal sheet in a magnetic field and pull the metal sheet with certain velocity v, then there will be a relative motion between a metal sheet and the magnetic field. That will give rise to the induced currents in the metal sheet. This induced current will form a circular loops, or they will flow in a circular pattern, and this circular pattern will resemble the eddies in water. And so they are called as eddy currents, or also known as the Foucault currents. The eddy currents flowing in the material will generate their own secondary magnetic field, which will oppose the coil's primary magnetic field. The applications of eddy currents. Eddy currents are used in induction furnace. Second application, electromagnetic braking. Third application, speedometer of the vehicles. If a given metallic sheet, and from that metallic sheet, if you can cut the strips from that metallic sheet, and if that same sheet is placed in a magnetic field, that is the changing magnetic field, no eddy currents will be generated. And this process can help us to reduce the eddy currents in the metallic sheets. Concept of self-induction. The figure shows a coil connected to a rheostat and a battery via key. The key is like a tap key. That means we can make and break the circuit so as to produce the changing currents. The changing current will act like an alternating current in the coil, and that will generate the alternating magnetic fields and will produce the EMF in the same circuit. The effect in which a changing current in the circuit induces an EMF in the same circuit is referred as the process of self-induction. So the alternating currents are producing the changing magnetic flux. The changing magnetic flux is getting linked with the same coil, as a result of which the induced EMFs are generated, and this induced EMF flows in the direction opposite to that of the applied one, and so this induced EMF is also called as the back EMF. The production of the induced EMF in the coil itself on the account of the change in a current in it is the phenomena of self-induction. Therefore, the magnetic flux that is linked with the coil is directly proportional to the current flowing through that coil. Therefore, if you remove the proportionality sign, you will get a proportionality constant, say L. Therefore, we can write down the above equation phi is equal to L into I, where L is called as the constant of proportionality, and it is a ratio of magnetic flux produced to the current flowing through the coil. This L is also known as the coefficient of self-induction. If the coil has n turns, then n times phi b is directly proportional to I. Therefore, n times phi b is equal to Li. Therefore, the coefficient of self-induction L is equal to n phi b upon I. The induction L depends on the geometry and the material properties of the coil. According to the Faraday's laws, E is equal to minus d phi by dt. So if you substitute phi as L times I, we get E is equal to minus L di by dt. In terms of magnitude, L is equal to mod of E divided by mod of di by dt. The SI unit of coefficient of self-induction is Henry. So we can define the coefficient of self-induction in different ways. Let us see the first definition. L is a ratio of phi by I. Hence, we can say that the self-induction of a circuit is the ratio of magnetic flux produced due to the current in the circuit linked with the circuit to the current flowing in it. The magnetic flux produced per unit current in the circuit is defined as self-induction. The second way I can define L is equal to minus E divided by di by dt. Hence, self-induction of the circuit is the ratio of induced EMF produced around the circuit to the rate of change of current in it. In simple words, the induced EMF produced around the circuit per unit rate of change of current in it is defined as the self-induction of the circuit. When the current increases in the circuit, an induced EMF acts opposite to it. Consequently, the work will have to be done in order to establish the magnetic flux associated with the steady current I0 in the circuit. Therefore, the work done in time dt can be written as Ei into dt. Substituting the value of E as minus L di by dt times I into dt. Dt gets cancelled, and so we get the work done equal to minus Li di. Therefore, the total work done is the integral from 0 to I0 minus Li di. Therefore, the work done is equal to minus L I naught square by 2. If we take that static current I naught to be unity, then the work done is L by 2. Or we can write L is equal to 2 times the work done. Hence, we can also define self-induction of the circuit as it is numerically equal to the twice the work done in establishing the magnetic flux associated with the unit current in the circuit. Therefore, the energy of the circuit is half LIO square. If we compare this with the kinetic energy of the moving body as half mv square, it's quite clear the role played by the mass in translational motion is the same role that is played by L in the phenomenon of electromagnetic induction. Mass plays or defines the inertia, L defines the electromagnetic inertia of the circuit.